And Sagar and since I was thinking
On Teams, it's not screen share.
yeah, yeah.
Is this fine? What is the used to?
Uh,
Is that one?
to close this, right? Okay.
Yeah.
Yeah. So Sagar here and Edvin. And we are presenting our work, like our seminar on knowledge distribution using early exit elements. Our focus will be on different types of confidence scoring. So just for we'll just discuss the original knowledge distribution work. So it was yeah, it was proposed by Hinton et al. In 2015. And the key idea here was that we have a large cumbersome model which is difficult to deploy. And so we are training smaller models efficiently from this larger trained models. And this is the workflow. We have a bigger model and we train a smaller model. The bigger model is the teacher model, and the smaller model is called the student model. So the idea is that the teacher model will provide like a student model with set targets, which help it learn from very less samples. So here, for example, if we train it on just the hard targets, which is just the 7 and 1, it's not very helpful. So we have already trained a teacher model. So we'll train to minimize this hard cross entropy loss along with the temperature normalized probability of the teacher model, so that it's able to also learn that the 7 is closer to 9 maybe, uh, even if the exact target is 7. So if we go next slide. So here we have like shown an example like these are the like they're usually trained with higher temperatures. Uh, so we see that the 7 and 9 if they are closer, and the student will be able to learn from much less samples from an already trained teacher model.
Okay, so also. Since we are focusing on the confidence margins, we thought it would be good to just start with introducing the original paper that we are starting with, co-authored by user. And we are basing the approach that we're looking at on the DGR model. If we look how this model works, it's not using the early exits to make the model faster, but rather better. And to do this, we have a teacher model which makes a prediction, and we have a smaller student model, and we're also using an auxiliary network in order to weight the loss function for the right samples in order to make the model work as good as possible. We see that the loss function is a combination of the cross entropy loss between the true sample, the true label, and the predicted label from the student model, and also the knowledge distillation loss, which is basically KD divergence, KL divergence to the power of tested temperature to the power of 2. We can go on to the next slide. What we found most interesting with this paper was that if we look at the worst groups, we see that the confidence of the model, how sure it is that it's predicting the right sample, is a quite high number, even though the predictions are often wrong. And that's what made us interested in looking at how can we improve the way we are using confidence margins in the model to make even better predictions. So we can move on to the next slide. Yeah, as I already explained, the loss function that are used in this paper is the cross entropy loss between the true sample. I don't have to say this one more time, and the KL divergence between the two models. The paper has tested on 2 image datasets and 2 language datasets, also classification. We are aiming to do our project more based on language. And what we can see is that the Didier model is making improvements, but in these hard cases, I have a slide on that coming a bit later, where, say for instance, that we're classifying a bird, and it's a land bird on water background. That's a harder sample to produce. But I have a good slide for that later, so we can move on. And yeah, we can go in a little bit to the model, how the model works for the original paper, that we're basically training a auxiliary network for every time we want to use it. And for some epochs, instead of just using the regular loss, we are training the auxiliary network in order to update the weights to make the overall training better. This leads us into what we are actually wanting to achieve. And the first paper that we're going to discuss to improve the confidence margins is called Fixing Overconfidence in Dynamic Neural Networks. Yes.
I mean, our paper also try to address this overconfidence.
Yes.
By actually having a network learn the weights.
Yeah.
How would you differentiate the approach there from the approach here?
Good. So we will try to focus on what ways we can change this paper is going to explain it quite well, what approach we're looking to take, but basically by changing the way the confidence score is calculated. This paper the objective of this paper is to decrease the computational cost by using a dynamic neural network and early exiting when we have a classification that is good enough. If we take the example that I have on the slide here, we have an image of a tiger that we want to classify as a tiger. And when the confidence of the model is high enough that there is a tiger in the picture, it will exit with the classification tiger. We can move on to the next slide. So it's a simple classification under budget restrictions. We have a training set with images in this case, and also the true labels. To address this problem, which was an optimization problem, we have a budget of how many floating point operational units we can use to achieve the highest possible accuracy. And we also have intermediate classifiers, of n here. And in order to introduce the notation for later, we will use, this is the function for the representation of the last linear layers. And we also have the weights of the model. So we are going to make the prediction on every intermediate layer using a softmax function, where we are basically doing this feature representation with the weights that we have in the last layer. We can move on to, the paper tries to differ between aleatoric and epistemic uncertainty. And aleatoric uncertainty is related to the randomness intrinsic to the task, and it cannot be reduced. For example, if we have an image that is maybe we are trying to classify if it's a tiger and there are both a tiger and an elephant in the picture, and we can only have output one layer. We are trying to target the epistemic uncertainty, which is related to knowledge of our task, which can be trained away with a better model. Oh, we can get on the last slide a bit. So what we are trying to address is these tricky samples. These are the aleatoric uncertainty. The model knows that it's hard to make the prediction, and it makes the wrong prediction. This is the case where the model is very certain that it's making the right prediction, but it's actually making the wrong prediction. Now we can move on to the next slide. What we are trying to do is that we want to make a Bayesian treatment of the parameters. So instead of having the fixed parameters at the last layer, we are sampling from a distribution of parameters in order to make better prediction. This is done with a Laplace approximation, and the map estimate can be defined by maximizing the function that we see here. So we are making our max on the log of the training data with maximizing over the parameters. This will work as the baseline for the model that we're using for sampling, where we have the LSM inverse as the covariance of. We can move on to the next slide. We are using a last layer Laplace approximation for the intermediate classifier of the deep neural network. The final prediction will be a sum of all the different samples we take of the logits in order to achieve a more correct how good the classifier, how certain the classifier is. The cost of using this in flops can be described as 2 times the number of classes times the number of and Monte Carlo samples, like how many samples we're taking from the model, plus the feature dimensionality to the power of 2, plus 5 times the feature dimensionality plus 2. The Gaussian distribution, we already showed it on the last slide, but this is another way of writing it. That we are having the mean of the feature representation of the last layer and using the Hessian inverse for the covariance. We can move on to the next. What we're seeing when we're using this type of model is that a lot of samples with using vanilla MSDNet, which is the baseline for the paper, is that a lot of samples is in this corner where the error is big and the uncertainty is low. So the model is very certain that it's making the correct prediction. What this type of model is doing, and this is the sort of the results, is that we're seeing a movement in the uncertainty going to the right when it comes to these tricky samples. So we are making predictions where fewer samples are both very certain and have a very high error. So it's a good progress for what we want to achieve with our project. We can move on to the next slide. The paper is not only looking at this confidence margin, but also trying to use an ensemble prediction of for every prediction, the prediction of every layer. We are making an ensemble prediction of all the earlier classifiers certainty, which is done in this way. It's a very simple formula.
Seems to be a cascade of priors. You start with the prior, then previous layers are adding prior to the subsequent layers.
Yes.
So that you don't have some upstart, right?
Exactly.
Reading from based on one of the intermediate layers, which is very confident about mispredictions.
Yes.
So this is kind of ensembling all through. But then the problem might be that this introduces a lot of bias, right?
Yes. We have not. We see that as a problem that we have to address. We don't have the solution yet, and we have not started experimenting with this.
But would that be your project?
Trying
to address the bias?
Trying to reduce the bias, but also trying to just benchmark this type of confidence margins in the year model from the original, together with the next paper that we'll also introduce. Yes, if we look at the results, especially for larger models, we see that the Laplace plus MIE, which is the ensemble prediction, is giving better results than the baseline model. We can see that we get better results using everything used is better than the baseline except for the Laplace, where in the case where we are not using MIE, but it's promising in the way that it's improving the results. Yes, the paper didn't mention anything mainly on tools, but also one that we are trying to look at is not an optimization. You know, optimization that increase accuracy. So we don't see it as too relevant.
So we'll look at the another approach uh, for confidence predictions, and this was based on like a paper by Razak et al. And it was published in UAI 2024. And the key idea here is they introduced this anytime valid confidence interval for uncertainty estimation in early exit networks. So, we'll start with like what are AVCS. So, say we have predicting confidence intervals from CLT-based methods. So, these methods are asymptotic in nature. So, as you have more and more samples, the statistical guarantees are given for asymptotic natures. And they suggest that instead of that, we want methods which are non-asymptotic in nature. So for any time, any sample. So samples here would be like exit at any layer, and we want these confidence interval to be valid. So guarantees to be valid for exiting at any layer, and so layer T, we have this confidence intervals LT and RT, and we train our usual networks with exit heads at each of the T layers. So we have T layers, and each of the exit heads has a specification head, the parameters of which are we are calling by W1 to T, and similarly U1 to T is the parameters for the layers that is, and we are just training over all the losses, predictive losses, and we'll come back to these things. So this is how they evaluate how good a confidence interval is for a solution. So first thing we need to check is what is the size of it. Like we want the size to be lower in most cases. Coverage probability. So say we are predicting YN. We want for our test samples, most of them should lie inside our confidence intervals. And we define this thing called nesting property. So we want the confidence interval to be nested. So the key idea is that since this confidence interval are coming from one layer to next layer, when we move from to a deeper layer, our confidence should actually increase. So this confidence interval should decrease. So we want this nesting property, and to see how good this confidence intervals are nested, we define theta star is this is just a parameter, and we want this is like a this is the guarantee that we want. No, this is this general parameter. For any general parameter, we are saying that this is the guarantee that we want, that our parameter should lie inside the confidence interval with at least 1 minus alpha probability.
So I have two questions. One is with respect to the paper you presented. I mean, there also there was a kind of prior. Now here the prior is very strong. Basically, you're saying the confidences have to increase.
Yes.
The intervals have to shrink.
Yeah.
See, but somehow, I mean, it depends on the task, right? If our paper which you presented, right? What one of the motivations of early readouts was that maybe you are over reading an image, right? You want to maybe classify. It's a aeroplane, right? But maybe there's a bird sitting somewhere in the image. The moment you start looking at some of the laster layers, the final layers, you're probably going to have entanglement of multiple signals. So idea behind early exit is also disentangle signals. Now, isn't this going against the grain of where an end task could actually determine early exits? Nested prediction seems to be in contradiction with early exit, at least for some tasks. What is your take? So there are 2 points. One is what's its connection with the previous paper, and isn't this an inherent or potential limitation? Does this work?
One thing that we wanted to address before looking at it was what difference we have to investigating what makes confidence margin. The papers are really different.
So that will also depend on the task, like for them. No, they were basically checking these evaluations on like CFAR, like how good are the confidence margins, like.
Okay. So see, Prateek, this makes good sense. I mean, absolute sense with all our learnings at Bharat and all. So this makes very good sense when you're doing pre-training a model. Right? As you go into subsequent phases, you want to get more confident. I mean, the phase 1, phase 2 thing is also kind of gelling. It's not just data phases, there's also network phases. So in pre-training, this makes sense. It's just that when you have a task, and if you're training towards a task, this possibly can be at loggerheads with the task itself. Is this for pre-training or yeah?
So we assume that the network was trained, like pre-trained, and then they just want the confidence margin for a test instance. It's not for pre-training.
Oh, so goal seems to be very different. You're a pre-trained network, and you're just trying to fine-tune it on a task.
Yeah. Of the prediction. I think so. For in their paper, the images, and they are assuming that you have a pre-trained network. Yeah. They are never changing the parameters of the network. No, they are not updating. Yeah,
So they're not
just
updating
giving.
any parameters.
They are assuming that this parameters have been trained.
Oh, then what is this coverage?
Okay,
Confidence interval shrinking. Oh,
yeah, because they are assuming that this classification head is actually Bayesian.
So this thing shrinking across layers is assumed or
no, they want to construct confidence intervals in such a way that the confidence intervals shrink, and they are
for a pre-trained network.
For a pre-trained network.
You want to train the network so that
yes, they are never changing the parameter.
Goal altogether. So you could just create softmax with basically you can create different temperatures, no? Isn't that equivalent to the confidence interval? Isn't it equivalent to in some form trying to find different temperature parameters for different layers?
Yeah, but the main claim is like they want this kind of guarantees anytime and at any exit you can have this guarantee, and based on this guarantee you can check. Like if you're not satisfied with it, you can go to the next layer and find the confidence margin for it.
But then you're saying this theta star is not even the current parameter; it's just any parameter.
Yeah, infinite task like. So this is a general framework which we want. This kind of guarantee we want, and yeah, we'll see like if we are satisfied with this confidence interval which we get, we can move on. Like it's like a early peak. Yeah, so this is how they will evaluate, and so for that to give these guarantees, they use this theorem called Will's theorem, and it's like a concentration type result, which says that if you have a martingale, so martingale is like any random variable which just the theta depends, like this random variable depends, expectation is constant, conditioned on the previous inputs, and the concentration result is that the probability of this going above 1 by alpha is very high. Like, it's like going above 1 by alpha is good. You can bound this. So this kind of statistical guarantees we want. So we'll construct this confidence interval based on this guarantee. Using this theorem, we'll just take all this r theta which is less than 1 by alpha. No, it's a we'll have to construct this for our. We have to construct such a martingale. Then we can use this theorem. So that will be our goal. And next. So to construct this, they claim that we will use this kind of like a Bayesian predictive ratio, likelihood ratio. So this is like given an input, with a test input. So we already have a pre-trained network given a test input, and WL is the exit heads, like classification head of the any exit layer, and they assume that this is like a random variable whose parameters are like set by the neural network.
So I just think, I mean, I find it more worth doing distillation and learning a student network than learning martingales. Because the degree of freedom here is very less, right? With martingales, you're dealing only with this confidence intervals. I mean, what is your thought? I feel it's very severely restricted in what the martingale can do.
Yeah.
As I guess being able using this model with frozen parameters as a teacher network, and actually, so there are some papers you have learned on student-teacher distillation. Yeah. Isn't that more worthwhile than learning martingales? But the paper you presented, its motivation was to be faster at inference. So I could learn a student network to be faster at inference also.
I think so. Yeah.
I think it's important to critique from multiple angles, I feel. Okay.
Yeah, let's move on. So again, they set trials for this sigma t will come from the network and sigma wt, and this wt will be decided when you are training it. This will be the parameters, and then you'll find the posterior for both, and then you'll take the ratio to get such guarantees. So let's go on next. And similarly, we have it for classification task. Classification task then our Bayesian framework is not on the weights, but on the classes. Is what an input takes. So again, we want to learn this alpha t from the networks. So yeah, so they claim that that learning those parameters for that display is actually difficult, and they'll just do a post hoc implementation. They'll take a ReLU on the at any exit, the ReLU of x with some random like this parameter, hyperparameter, which they'll choose from the validation set. Yeah. So this is like their comparison. So this is like a normal base, like another method, and these are the training points, and this is the confidence margin which they're giving. So for this method, the confidence margin is actually bigger, but then we have like better guarantees. That's what the claim is. So next. So
it is not necessarily smaller the confidence margins.
Yeah.
The lesser the more the guarantees or less. I mean, there's no correlation.
Yeah. So,
but what's the overall take home, right? I mean, with respect to confidence intervals and
so like any other confidence interval, if we create, we have like asymptotic guarantees. Here we have like at each layer we can give like strong guarantees. And based on it, we can see like if we want to move to the next layer or not. So that's what they claim. So the nestedness is very high for our method, and it's low. Like as you move beyond the layers, the nestedness decreases, but ours remains 1. Well, the coverage, if you see, like it decreases, but then it's good. So this is expected. The main thing is this one. So our interval size is bigger. certainly than other methods because we are taking very weak assumptions, and it's non-asymptotic. But then soon as we go to later layers, it's almost close to the one by other method. That is the key takeaway. Yeah, this is based on CFAR 10, 100 and ImageNet. So this was the proposal then. So our proposal is how can we use confidence margin to improve the student model, to make the student model learn efficiently. And we want to try both of these approaches, AVCS and Laplace approximation, and try to see if we can try these approaches on newer LLMs. Yeah, but yeah.